Okay, so circuit is given here, and we are asked to determine the real and reactive power losses and the real reactive power being supplied. The power is 0. The load is 40 kilowatt. This is the active, the real power, or active power, and the power factor is 0.84 lagging. It has current flowing through it, IL, and voltage across it is, or VL, is 220 volt with the phase angle of 0 RMS. And the transmission line has an impedance of 0.1 ohm plus J 0.25 ohm. Power factor 0.84 lagging, so the current is lagging to the voltage by 0.84. So it means it is an inductive load, because current is lagging from the voltage. So the power, we are asked to determine the real and reactive power losses and the real and reactive of the power being supplied. So the power is equals the real part of the complex power, the active power, and this equal to the magnitude of the complex power multiplied to the cosine of theta v minus theta I at the load. And theta v minus cosine theta v minus theta I is basically the power factor. From here, then we can calculate the magnitude of the complex power at the load. Here equals to the power 40 kilowatt divided by the power factor. 40 kilowatt divided by 0.84 equals to 47.62 kilovolt ampere. So please be careful that this means when the unit, when we are speaking about complex power, then the unit is volt ampere, not watt. Then the magnitude of the reactive power loss at the load becomes from here, then is reactive power is the Q part, the imaginary part of the complex power. So then from Pythagoras theorem, we can calculate it to be equals to the square root of the magnitude of the complex power squared minus the square of the active power. So from here, so this goes to this 47.62 kilo squared minus 40 kilo squared. So then we obtain 25,839 volt ampere. Since we know that complex power equals to the voltage times the conjugate of the current, so we can calculate now the magnitude of the current equals to the magnitude of the complex power divided by the magnitude of the voltage at the load. So this means that the magnitude here is this one, 47.62 kilovolt per kilo divided by 220 volt, and then we will obtain 216.45 ampere. So this is the magnitude. And since the power factor is 0.84, so theta v minus theta I equals to arc cosine of 0.84, and we will obtain 32.86 degree. So like this, so the theta v minus theta I equals to 32.86 degrees. And then IL will be equals to 216 point, this one, the magnitude here, 0.45 degree, angle of minus 32.86 degrees. So because here, since it is lagging, the current is lagging from the voltage by 32.86 degrees. The S losses equals then to the loss at the transmission line equals to the impedance of the line times the IL. This becomes the voltage of at the transmission line, V transmission line, multiplied by the conjugate of IL, or then Z equals to Z line multiplied by IL times the IL conjugate. IL times IL conjugate equals to the IL squared, the magnitude of the current flowing being squared. So the S losses, the complex power loss will be equals then to Z line equals this one, 0.1 plus J times 0.25 multiplied to 216.45 squared. Yeah, the magnitude of this IL is this one, 216.45 V squared. Then we obtain 4,685 ampere plus J 11 volt ampere plus J 11,713 volt ampere. So since we want to determine real and reactive power supplied by the voltage source, then there should be a balance of power. So the complex power supplied should be equals to this S losses, complex power loss plus the complex power at the load. Okay, S supplied equals to the S losses plus S load for 4,685 plus J 11,713 volt ampere plus which one is the magnitude of the complex power at the load? This one 47 or 40 kilowatt plus J 25,839 volt ampere. So we obtain 44,600 in kilo, yeah, 44.685 plus J 37.552 kilo volt ampere. Okay, so this is from the balance of power. Okay, another example now. We have another load with power factor 0.85 lagging, and the actual power, the active power is 60 kilowatt. The voltage at the loading is 220 volt RMS with phase angle of 0. Transmission line has an impedance of 0.12 ohm plus J 0.18 ohm, and we are asked to determine the line voltage here, VL, and power factor at the supply N. Okay, so we have to determine IL. Okay, then by multiplying IL with the impedance at the line, we will obtain the line voltage. Then to obtain the power factor at the supply N, we have to determine the angle. We have to determine VRMS at the source, yeah, at the supply, including the angle and the theta V here, and we subtract the theta V here with the theta I of the current IL here. Then we take cosine of that angle difference, theta V minus theta I of the current here, theta IL. Okay, so the power equals here 60 kilowatt will be equal to the real part of the power of the complex power at the load. So SL equals to the VL times the IL conjugate. So IL means equals to the magnitude of, or here equals to magnitude of S cosine theta V minus theta I equals to VL times IL times the power factor. So magnitude of IL will be equals to the magnitude of S, yeah, or equal to the power here divided by magnitude of VL divided by the power factor. Yeah, so this equals to 60 kilowatt divided by 220 volt divided by the power factor 0.85. Yeah, we will obtain 320.86 ampere RMS. Yeah, so this is how it looks like in the phasor diagram. This is the voltage RMS 220 volt. The current IL RMS is lagging with the power factor of 0.85. So this is basically cosine theta V minus theta I. This is the IRMS. The actual power, the active power is 60 kilowatt, is VRMS times IRMS cosine theta V minus theta I. And the reactive power at the load is here, IRMS sine theta V minus theta I. So theta V minus theta I equals to arc cosine of the power factor 0.85. So this theta V minus theta I equals to 31.79 degrees. IL will be equals to 320.86 ampere RMS with an angle of minus 31.79 because this lagging. or this equal in the complex format as 272.72 minus J 169.03 ampere RMS. Now we obtain already now the IL, the current flowing through the circuit. We are asked to determine the line voltage. The line voltage will be equal, or the transmission will be equals to Z line times the IL. This one. The voltage, the source voltage, will be equals to this Z line times IL plus the voltage at the load, PL, 220 volt RMS. Then this equals to 0.12 times plus J 0.18 multiplied to the IL, this one, 272.72 minus J 169.03. You can do direct calculation, or you can change to Phasor format first, then multiplying it. Yeah, you can do it different ways. Plus 220 the voltage at the loading. So we will obtain the voltage at the source equals to 283.15 plus J 28.81 volt RMS. Okay. Are you still following, or everyone sleeping?
Following, sir.
Still following, sir.
JC and Martin. Okay, the rest? Sleeping.
Still following, sir.
Sleeping, then we can have a sudden quiz.
No, not again, sir.
Okay, yeah, so then we can express this also in Phasor format. Yeah. 284.61 with a phase angle of 5.81 degrees volt RMS at the voltage source. And we are asked to, this is the voltage at the source, yeah, and we are asked to determine the power factor at the supply end. So we draw the Phasor diagram. So this voltage source, this angle 5.81 is relative to the voltage line, voltage at the load, yeah, because here the reference is the voltage at the load. Here we have 220 and with the phase angle of 0 degree VL. Right? So this 5.81 is leading relative to the VL. Well, the current IL has the phase angle of minus 31.79 degrees, so lagging towards the VL. So the difference of the phase angles between VS and IL is 5.81 minus 31.79 degrees, or 37.6 degrees. So the power factor equals to cosine of this 37.6 degrees, or 0.972. Lagging means the current is lagging towards from the voltage. Okay. Okay. So now we move on to a new subject or new concept called as the power factor correction. As we have learned from power factor concept, yeah, in the previous section, that when the power factor is much less than 1, then we will have a lot of power loss, yeah, in the transmission line. And the low power factor at the load will increase the loss, yeah, because then when you have low power factor at the load, the IRMS will be high. When it is high, then when it is multiplied to the impedance of the transmission line, the power loss becomes high as well. I square, yeah, I square times the Z of the line, the impedance of the line. Typical industrial loads are inductive, yeah, because of the coiling, etc. Yeah, because of the wire itself. Yeah, like transformer, this one is inductive due to the coiling. So to compensate that, usually we will have power banks made from capacitors, so that then we will have a compensating capacitive reactance, capacitive reactive power that will reduce the inductive reactive load, so that then we will make the theta V minus theta I approaching to 0, or the cosine of that which is the power factor, will be closer towards 1. So then the power loss will be also less, bit less. I think you have done this in your practicum, in your practical work experiment, albeit by simulation. So this is the concept. In typical industrial load is inductive, so we will have this SL as the complex power, and as a result, then many power loss due to this the magnitude due to this QL, the reactive power, inductive. So to make it closer to pure resistive, also we compensate with this QC, so that then the eventual complex power becomes reactive power becomes this QL minus QC. So a simple approach to correct power factor is by putting a parallel load with a capacitance here. So normal industrial load has a lagging power factor. Yeah, the voltage, the current is like the voltage because it is inductive. Mostly it is inductive load. Then to compensate that power loss due to that lagging power factor, to make the power factor higher, closer towards 1, we put a parallel capacitance. So without the capacitor, the old complex power will be S old equals to P old, the active power, plus JQ old, the old reactive power. Or in phasor format, it's become the magnitude of the complex power, the magnitude of the old complex power, S old, with the phase angle of theta old. Yeah, in this case, in this figure, it is drawn here in this first arrow, theta VL minus theta IL. The power factor old is cosine this theta old. Then we introduce a capacitance parallel to this. And we know that the impedance of capacitance is 1 over j omega c. So the voltage at the load will be equals at the capacitance load here equals to the current flowing through the capacitor, I capacitor, times the impedance of the capacitor times 1 over j omega c. And this is leading, yeah, it makes when you multiply, the voltage is lagging. The voltage is lagging from the capacitor, or the current is leading the voltage. So this will compensate the lagging power factor due to the inductive load. So the Q capacitor, the reactive power due to the capacitor will be equal to the voltage L multiplied with the magnitude of the current of the flowing through the capacitor. Or if we replace this VL, the magnitude of VL with this one, basically the or the I capacitor, yeah, the I capacitor we substitute with this one, so it means then if we derive it, so the I here capacitor equals to VL, then this is J omega C, right? The magnitude then will be equals to the VL square omega C. So this is what is being so no, there is no square here. Yeah. So the magnitude of this current is VL omega C. Yeah, so this has the current means, since this is J of VL omega C, means the current leads the voltage by 90 degrees. Okay. So the magnitude of the reactive power of the capacitor is equals to magnitude of VL times this current, so times VL times omega C, of VL squared times omega C. So then with capacitor, the new complex power will be equal to the old complex power plus the capacitor complex power. Okay, so this means this P old plus JQ old minus JQ capacitor, the reactive part. So this is only reactive. The capacitor only contributes reactive power. Yeah. So since this is the capacitance here is is leading, yeah, has a leading power factor. So it means the voltage is lagging the current. So it has this negative reactive power. So the new complex power will be equal to P old plus JQ old minus JQ capacitor. So this equals to the magnitude of the new complex power with an angle in phasor format, yeah, with a phase angle of the new. And the new phase angle is this one. So this is the original QL. Then after negative QC, this becomes this QL minus QC. So here we have a smaller theta V, theta VL minus theta I. Smaller means then the cosine of this smaller angle will be closer towards 1. So we have a higher power because we have a higher power factor. The power loss is then reduced. So the tangent of this theta nu equals then to the Q old minus Q capacitor here, the imaginary part or this part, divided by the old power, the active power, or cosine theta equals to from trigonometry 1 over square root of 1 plus square of tangent theta. Okay, so let's do some example here. The economic impact of power factor correction. So it is common for an industrial facility operating at poor power factor to be charged more by the electric utility providing the electrical service. Why? Yeah, because then the current IL will be larger, yeah, then it will create more power loss at the transmission line. That's why then the electric utility company will charge more. For example, here, operating condition at 277 volt RMS and requires 500 kilowatt at the power factor of 0.75 lagging, so it is inactive load. The energy charge is 2 cents per kilowatt hour and a demand charge of $3.50 per kilowatt per month of loss if the power factor is between 0.9 lagging and unity, and $5 per kilovolt ampere per month if the power factor is less than 0.9 lagging. So current monthly utility, the energy charge is then 500 kilowatt times 24 hours times 30 days per month. So this is kilowatt. If it is 1 hour, then 500 kilowatt hour times 24 hours per day times 30 days per month times 2 cents per kilowatt hour. So they have to pay, this industrial facility has to pay $7,200 per month. See, then the complex power before of all before introducing any capacitor is the 500 kilowatt here divided by the power factor 0.75 with an angle of cosine 0.75. Yeah, so then this is because this times this cost lagging factor is the actual power. So then the magnitude of the complex power is 66.67 volt ampere with a phase angle of arc cosine 0.75 here, or 41.4 degrees. So this is quite low power factor. This equals in complex format as 500, the active power, plus J 441 kilovolt ampere. So here we see that the reactive power loss, reactive power is quite high for 141 kilovolt ampere. So then the demand charge will be equals to this magnitude, kilovolt ampere, times the $5. This is the additional charge. Is $5 per kilovolt ampere per month if the power factor is less than 0.9 lagging. This is the power factor is less than 0.9 because power factor is only 0.75. So they have to pay $3,333.35 US dollar. If then the power factor is corrected to 0.9 by adding an additional capacitive load, okay, then the new complex power will be 500 kilowatt divided by 0.9 with the phase angle of cosine 0.9. So this new complex power will be 555.6 kilovolt ampere with a phase angle of 25.84 degree, or in complex format equals to 500 plus J 242.2 kilovolt ampere. See here that the reactive power is smaller. Instead of 441 kilovolt ampere becomes 242.2 kilovolt ampere. The new demand charge will be, since now the power factor is increased to 0.9, so they are only being charged $3.50 per kilowatt, so only $1,750 per month. So the saving that this industry can make is this amount minus this amount, $1,853 per month. So just by adding a capacitor bank. And the additional energy charged to the capacitor bank is negligible, but they can save a lot. Okay, let's give another example. Determine the capacitor required to increase the power factor to 0.95 lagging. Okay, so we have here an induction motor, and the active power is 50 kilowatt. The voltage at the load is 220 volt with phase angle of 0 degree RMS. Power factor now is 0.8 lagging. So the power is real of S, so which is equal to the magnitude of S cosine theta V minus theta I. So you can calculate the magnitude of S by P divided by the power factor. P divided by cosine theta V minus theta I. 50 divided by 0.80, we obtain the complex power to be equal to 62.5 kilovolt ampere. Okay, so then the magnitude of the reactive power due to the inductive load here is equal to S squared, magnitude of S squared minus the active power squared, then taking as a root of that value. We obtain the reactive inductive power to be 37.5 kilovolt ampere. And since now we want to increase it to 0.95 lagging, we have to find the theta nu. So from here we obtain tangen of theta nu equals to square root of 1 minus the PF square nu divided by PF. Then we obtain 0.329. This is from the formula that we gave in the previous slide. Okay. So the tangen theta nu, if you look from the phasor diagram, tangen theta means the y over x. So the q divided by the p, the q nu divided by p. So if we find it difficult to memorize this formula, just find the theta nu first, and then the angle, and then you can calculate the tangen theta from that angle. And this equals to 0.3. The new reactive power divided by the active power too. So from here, then we obtain the new reactive power equal to tangen theta times P, 0.329 times the power, and the power here is 50 kilowatt, and then we obtain 16.43 kilovolt ampere. Okay, so from here, then we can calculate the capacitance. The Q capacitor here will be equals to Q alt, which is this one, 37.5 ampere minus 16.43. So the reactive capacitor power is 21.07 kilovolt ampere, and we know this is equal to voltage square times omega c. So this is divided by the 220 square, this one, divided by omega c to pi to obtain the capacitance, 2 pi, and the frequency is 60 hertz, the frequency of the transmission line, and then we obtain the value 1156 microfarad. Okay. Another example, determine the capacitor necessary to increase the power factor to 0.94. The old power factor is 0.707. The active power at the load is 100 kilowatt. The load voltage is 480 volt RMS. The transmission line has a resistance of 0.1 ohm, pure resistive. Frequency is 60 hertz. Okay, so now we have to determine first the Q, the old Q, and the S, the complex power. So the power equals, the complex power will be equals to the P divided by the power factor. Okay, 100 kilowatt divided by 0.707, you obtain 141.44 kilovolt ampere. Then we obtain the Q alt. The Q alt will be equals to the, from Pythagoras, square root of the S, this value square, minus the value 100 kilowatt here squared. We obtain 100.02 kilovolt ampere. So then when the new power factor is 0.94, then we calculate the theta nu. From there, after we obtain theta nu, we calculate tangen theta, which is of that new theta, and we obtain 0.363. From here, we calculate the new Q, the Q nu. Yeah, the Q nu is the Q, the power, the power times that tangen theta. Okay, so this Q nu equals to 0.363 times the active power. So we obtain the Q nu to be 36.3 kilovolt ampere. We compare with the Q alt, this is reduced significantly. Okay, and this is obtained from the additional capacitive load. So the Q capacitor equals to this minus this, okay, or equal to 63.72 kilovolt ampere. This is equal to L square times omega c. So to obtain C, we divide this 63.72 kilovolt ampere by TL square, 480 volt square, divided by 2 divided times pi times the frequency 60 hertz. Then we obtain the capacitance value, the additional capacitance value, 733 microfarad. Okay. Are there any questions so far? If not, then I would stop here, and we will continue maybe with single phase reverse circuit concept next week.